My name is Saïd Ramani. I'm a PhD student at École des Mines, and I'm going to speak about characterization and estimation of the variation of the grain of the Boolean model. First, the geometric stochastic modeling and the objectives. Several materials present random nature in the sense of they are composed by several random particles, and their geometry is closely linked to the physical property of these materials. So we need to understand the geometry of this structure. When the GEMGRAIN model was born, it's defined as a union of a random convex set centered on a point process. The random convex set are assumed to be identically independent and identically distributed. And in this model, the distribution of the point process represents the spatial distribution of particles, and the distribution of the primary grain represents the granulometry. The simplest GEMGRAIN model is the Boolean model, where the point process is a Poisson point process. The objective of this model is to obtain a geometrical characterization of the grain from measurements of a global model in a bounded window, because we often work with images. We want to make no assumption concerning the shape of the grain and to obtain a characteristic describing shape and size of the grain. In order to do this, several existing methods can be used to obtain first-order moments of Minkowski content, so the area of the grain and the perimeter. So the theoretical aspects. So if we take the grain having the same shape, they are all homothetics. The first order moment of perimeter is connected to is proportional to the homothetic first order moment of the homothetic factor, and the expectation of the area is proportional to the second order moment of the homothetic factor. So we can put a parametric distribution of this homothetic factor and characterize the model. But if we take grain where the shape can be also random, just a little more complex grain like a rectangle, we see in these two images, but for same mean area and perimeter, we have a really different structure. So in order to characterize the grain, we need to define and estimate the variation of the shape of the grain. I present first the theoretical aspects and later application. In order to make it appear the variation, we have to work with covariances. It's a global characteristic, also called 2-point probability function. It's a probability of model hits 2 points. It can be estimated as a fraction area of the translation of model. And it can be connected to the mean covariogram as the expectation of the covariogram of the grain, the same quantity but for the grain. We have a relationship to connect these two quantities. And an important property of the mean covariogram is that its integral under the space is equal to the second order moment of the area of the grain. So this is a variation, and we work with this quantity. And by a deformation of the model, we can extract several other variations, geometric variation. The Boolean model is present as a kind of stability by dilation, in the sense of if you take a Boolean model and dilate it by a convex set, we obtain another Boolean model with same intensity associated to the dilated grain. So all we can estimate for the grain, we can estimate for the dilated grain. By taking a family of homothetic convex, we can estimate the second order moments of the area of the dilated grain. And by the well-known Steiner formula, the area of the dilated grain can express as a polynomial function, where the W0K is the so-called mixed area. I explain later the interpretation of this quantity. So by developing this second order moments, we obtain a polynomial function, and by classical polynomial fitting, we can extract the second order structure of a vector composed by area and mixed area of the grain. Of course, it can be generalized to any other moments, considering not the covariogram, but the n-variogram, the translation of a set for several vectors. And this n-variogram can be connected to the endpoint probability function. So finally, we can estimate all moments of vector composed by area of grain and mixed area. The interpretation of the mixed area, it can be defined with a Steiner formula. For a ball, the mixed area coincides with the perimeter, and for segments, with the Ferret's diameter. Ferret's diameter is a measure of set with a, I don't know the English word for Piaculis. And an important property of this mixed area, it presents this kind of linear property between Minkowski addition and with a Minkowski addition. If we take a convex construct by the addition of several segments in several directions, we have a linear combination of the Ferret's diameter in each of those directions. So by taking the moments of this quantity, we can have all moments of the random vector composed by Ferret's diameter in each direction. So we can characterize the random process, the Ferret's random process, the random process associated to the Ferret's diameter. And this random process can be used to describe and characterize the sets because one of this realization is a function, and the best function describe totally the symmetrized grain. So we have a functional description of the grain. And furthermore, if the grain is isotropic, the Ferret's process become stationary. So we can use all known tools for concerning stationary random process for describing random convex sets. The practical aspects are more difficult. In practice, it's not easy to go to n order moments because it takes a long time calculation. So we go to first, second, maybe third order. For the second order, we have this quantity considering the element of dilation as a disk segment or parallelogram. So we have the red quantity. The procedure of estimation can be described here. We take one realization of a model in a bounded window, a chosen element of dilation K, and a chosen family of radius for dilation. We dilate our realization, taking care to take it in the eroded window to break the edge effect for all radius. And then we compute the covariances with, and then with the analytic formula, we have the mean covariogram of the dilated grain. And then by an integration, we have the famous second order moments of dilated grain. With polynomial fitting, we have the estimators. There are several questions concerning the discretization in projects of sets, the number and size of the radius we take. So, in order to be optimal on the estimators. For the statistical aspects, it's well known the estimator for covariance is unbiased and consistent. Of course, it follows a consistent estimator for the moment we assume, but not necessarily unbiased. But we take hypothesis of small bias for the grain, for the window bigger than the grain. And we have tested this by simulation. Now I present some results. We have simulated several realizations of the following model. We have, there are almost in mean 100 grain in the window. And there are rectangular grain where the side follow normal distribution. And we have taken 10 elements of dilation. With segments and with a disk. Here I represent the relative error between on the estimated in function of the number of realization we take to make our estimation. We can see for 1,000 realization, make almost 5%. As a conclusion, we have a theoretical estimator for the random process, It describes symmetry Z grain. But in projects, we have estimation of first and second order moments of random vector area perimeter and area phase diameter. And that is sufficient to characterize random particle depending on two parameters. We have a shape depending on two parameters, rectangle or ellipse. We prospect to describe more complex shape by using the autocovariance of the random process and its mean. Maybe with the Gaussian random process. And we prospect also to work with, to attempt to quantify the anisotropy of the model. And we hope to have the Bayes corrector. So, thank you for listening.